So our next speaker is Marc Rivinius from University of Stuttgart. Marc is an expert in multi-party computation, and today he's going to take a look at specialized preprocessing for maliciously secure MPC. So floor is yours. Thanks, Marc, for coming.
Thanks, Ahmad. My talk is about preprocessing MPC, more specifically maliciously secure MPC, and also then focus on preprocessing for matrix multiplications and convolutions. So that's why I first want to start just to give like a quick recap what kind of convolutions we mean here. So this is like a basic example, 2D convolutions. The gray thing on the left is an image. The blue thing in the middle is a so-called filter. And the convolution works in a way that you align the filter on top of the image. And every pixel that overlaps, you multiply the image value with the filter value. Then you sum them all up and you get one pixel for the output. And then you move over your filter one step, you get another pixel for the output, and you can move over until you cover your whole image. You can then so-called pad your image, just define some values outside, usually just 0, and continue that to get, for example, like a filter that's as big as your image, because a lot of use cases just use that. So you don't get smaller and smaller if you do more convolutions. So overall, it's just some operations that is linear, and you have like as many multiplications and additions for every output pixel as your filter is large. And yeah, there is also some multiple ways to represent this as a matrix multiplication. And one more or less intuitive way is that you do again the same thing, and to do your convolution now as a matrix multiplication, you just put all your filter elements in a vector, you put the corresponding image elements in a vector, then you do a dot product and you get one part for your output. Then you move over your filter one step, you get a second vector, and then you basically just build all these vectors for your image, you put them in a matrix, and overall you have like a matrix vector product to get the same result. But you might notice here you get like an overhead because you have a lot of repeated elements in your matrix. So that's already getting a bit ahead, why later if you do directly convolutions, it's better than going through matrix multiplications. So now just a quick description of our setting. We want to do MPC, so multiple parties want to compute a function together. Usually if you're talking about convolutions or matrix multiplications, it's likely that you're you have like a machine learning use case, and then something MPC could be some parties have some of the input data, some parties have like the machine learning model or the weights of the model, and they want to just evaluate the model together. And then in the basic setting for MPC is semi-honest, so the adversary can observe some information on the network and on some of the parties, and maliciously secure. We just also some of the parties can misbehave arbitrarily, and we still want the correct result or abort, and keep the inputs of the honest parties secret. So one family of protocols that does that is the speeds protocol, and a lot of derivatives that build on that. It's relatively efficient, and especially for the use case where you have an arithmetic circuit, so arithmetic operations, for example, convolutions, compared to like Boolean circuits. Also for dishonest majority where all but one party could be misbehaving. And yeah, the building block is secret sharing. We just the share notation here, share with the brackets and the party index as subscript. The secret is then the sum of the shares, and we can do all linear operations on shares without interaction. And to get the malicious security, Speeds uses authenticated secret sharing. So we have max on the secret shared values, where we have a secret MAC key alpha that none of the parties know. And an authenticated share is then the share of the value and a share of alpha times the same value. And then there is a MAC check procedure to check every value that is opened as intermediate value and check every output. And if some parties cheated, then you can detect that with the MAC check. And yeah, because we have the linear secret sharing, also on the MAC'd version, on the authenticated secret sharing, you can still do all the linear operations. And then the basic procedure that you do in Speeds is, because you can do linear operations basically for free, you convert your whole circuit in something that is mostly built out of linear operations, and opening in the intermediate values, because that's what you can check with the MAC check. And to do that, you prepare correlated randomness, where you basically just have specific random values that you already prepared an authenticated secret sharing for, and then you can use that later. I show in the next slides like how this is usually done. It's like the basic technique are so-called beaver triples. Here the goal is we have an authenticated share of two values, x and y, and we want to get the authenticated secret share of the product. And as I said before, we have only linear operations, and we want to use some correlated randomness for that. So the correlated randomness is this triple ABC, where A and B are uniformly random, and C is the product of A and B. And then every party has their share of that. Then the first thing the parties do is open masked versions of their inputs. So X minus A, they can compute a share of that and then open it. And the same for Y, Y minus B. Then they get these public values U and V, and they don't leak any information because A and B are uniformly random. And then the beaver multiplication is just that here in the first line, this linear combination of the shares of A, B, and C, and you multiply A with V and U with B, and then also add the product of U and V, and just if you write it down, it all works out. You get a share of X times Y, because the parts that depend on A and B just cancel out. And the nice thing about this is it also works for matrix multiplication. So you basically just change your X and Y to matrices, your A and B to matrices. Now C is a matrix product of A and B, and your result will be a matrix product of X and Y. And you can also do it with convolutions, because convolutions are also bilinear operations. So you just change the operation here, but the basic procedure you can still do. Just now your task is to, so your goal is to have the matrix multiplication or convolution, and then the task is what you have to now do efficiently is to do the preprocessing, so generate this convolution triple or matrix product triple in an offline phase, so you can use it later to do this in the online phase. It works for any bilinear operation. There's also a version when you have like just one input, for example, squaring, or like doing the product of a vector with the transpose of itself. For example, if you want to compute a norm or dot product. It works more or less the same for these operations with one operand, and you just need pairs. There's also version for basically any polynomial, which is also quite nice. But here you have the problem that you don't have a triple anymore, so 3 elements you need to process, but it's growing exponentially in the degree of the polynomial you want to do. But in general, you can not only do it for these simple linear operations like multiplications or matrix multiplications, but even things like polynomials, and you can extend this probably further to do like polynomials of matrices and other related operations. We also had recently a paper where we do this slightly different, and then you don't have an exponential overhead anymore, but just something like log linear, but I don't talk much about that in this talk here. So why do we do that in the first place? Can't we just do everything with the normal Beaver triples? So like break down all the matrix multiplications and convolutions into scalar multiplications and do them with Beaver triples. Like if you would do that, you can do that, and that's what people did because that's the natural thing, and a lot of frameworks don't support like special operations for matrix multiplications, at least at the time we worked on the paper. Then one thing is the overall overhead is quite large. So here's for communication, which is like the main bottleneck of MPC. A lot of the times, if you break down here in this example for the ResNet 50 machine learning ML model, you just look at all the convolutions, ignore the rest, and figure out how many multiplications you would need. You get like almost 58 gigabytes of data the parties have to send. If you then represent the convolutions as matrix multiplications and use specialized matrix Beaver triples, you're at like 450 megabytes, and with the convolutions around 210. So that's like 2 times overhead if you go through the matrices, and that's mostly because of the thing I showed at the beginning, that if you represent the convolution as matrix, it has some repeated elements, and you don't have this repetition as overhead that you need to communicate. And if you break down everything in individual multiplications, because a single element is used a lot of times in a convolution, and if you do then only the scalar Beaver triples, you have like almost 290 times overhead. And we also did some benchmarks like for the runtime. It's not as big of a difference here in our tests, but still you get significantly faster if you do some kind of specialized operation. And especially then if you have a slower network, then the communication overhead gets more and more visible. So on the left is like a faster local area network, and on the right is slower network. And here you have like 27 times faster than the individual Beaver triples, and around 12% faster is convolutions compared to matrix version. And that's just the online phase. The other thing is then the offline phase, where we generate these random Beaver triples. That's another thing where it's important how you do it. So the general way or classical way is just to use homomorphic encryption, because in the offline phase we say that's less time critical. You can do it in advance. It doesn't depend on the inputs. Every party chooses basically a random number, and you do like you do a convolution or a matrix product on these random numbers, and you have some small protocols around how you get from like one homomorphically encrypted product to like shares of random numbers. So the standard approach basically just does that. You have some input vector. You need some way to encode it in something that you can encrypt. You do it for a second vector. So these can be like the A and B for our triples. Then you can do SIMD operations usually in homomorphic encryption. You get another encrypted vector, you decrypt it, decode it, and here you get the sum, but we want to do that for multiplication, so we do some just ciphertext multiplication in the middle, and we would get at the end like a component-wise product. So we can use this for standard Bieber triples. And usually it's more efficient if only one of the operands is encrypted, and there are like special, basically two-party protocols where one party sends the encryption to the other party, they multiply with their vector and send it back in a masked way, then they can decrypt it and they get shares of the product, which is exactly what we want to do. That's a two-party case. You can extend that to any number of parties. And you basically get the normal way for doing this for Bieber triples. You can do that more generally. Instead of just encoding everything in like SIMD vectors, you store your data in a clever way in the encrypted vectors. You can do more than just one multiplication or an addition in the middle on your ciphertexts. And then you basically just, what we do is we just choose a clever way to put our things into ciphertext, so we get a matrix product or a convolution out at the end. And it's general enough that it works with both encrypted or mixed encrypted inputs. So the main idea for what we do for convolutions reuses the fact that a lot of the operations that you do on ciphertexts in lattice-based encryption schemes basically do cyclotomic work in cyclotomic polynomial rings and do multiplications in there. So that's basically for BGV, which is a lot used in speech protocols. That forms a plain text space here. So you get your operations, your operations on ciphertexts map very easily to just these polynomial multiplications. And like if you have a polynomial that maps to a vector of n elements by just the coefficients, if you have then two polynomials and you want to multiply them, it looks somehow like this. If here the colored elements are the non-zero coefficients, then to multiply them, you wrap around your one of the operands, you multiply all the coefficients that overlap, you sum them up, you get the first coefficient of your result, and then you rotate around your polynomial cyclically, you multiply again, you sum them up, you get the second coefficient, and so on until you're done with all of them. And that's a so-called negacyclic convolution, and obviously it's very similar to a convolution. One difference is that it's cyclic. You don't you need that usually for the applications that you're using. And the negacyclic means every time you wrap around, you multiply also with -1. You don't need that, but that happens at usually also the places where it wraps around. You don't want that, and that is negative. You don't want, so you avoid that just at the same time. So that doesn't make much difference. So this is basically also just like a 1D convolution. You can extend that also to higher dimensions. And that's like one example. What we did is like if you have like a more complicated so-called conv2D, which is not just a 2D convolution, but like a sum of multiple 2D convolutions, where you can have multiple batches of images with different channels, then a lot of different filters with some number of channels that matches the input image and some number of channels that matches how many output images you want. Basically what you want to compute are individual 2D convolutions where these channels match, and then sum them up as well to get one of the output channels. one of the output images. And then, yeah, you just do that for all of them. So we not only want 2D convolutions, but we want multiple of them and sums of 2D convolutions. And yeah, it turns out you can, if you save your image and filter in the right way in the slots, you still get all of this just by one normal polynomial multiplication, basically. So if you line them up like this, so first everything of the first batch of the image, and then you leave as much space so it is exactly as large as your filter if you would put it in there, and then start with the second batch of the image, and your filter you basically just linearly write in your coefficients, but you have to also flip it around, because when you multiply it, it flips around again. You get the conv2d operation that we wanted. So if you would do the polynomial multiplication again, you would first get this, that you have like some non-matching or things that we don't want multiplied by each other. And then you rotate around, gets more, but at some point the right channels of the image and the filter overlap, you multiply them, and you get one part of the output that you actually want. Yeah, and then you continue until you get all the parts of the result you want, and your unpacking is basically just extracting the right slots. Yeah, here we show how much that can save us compared to another paper that directly produces matrices or matrix products for triples. Here also we're 5 times faster than the matrix approach and 28 times faster than the scalar Beaver triple approach, and even more for the Beaver triple approach in the slower network. It's still 3 times faster than the matrix-based approach. Yeah, and the nice thing about this is if you look at how the matrix-based approach does this, they mostly do it just in FHE, so they use a lot of ciphertext rotations and maskings, so the right things overlap, and we just do it directly in one operation where we don't have to do any additional operations on ciphertext. So that saves us a lot of basically compute time. Yeah. No, that's, I think, extrapolated. Yeah, because here it's all individual Beaver triples, so you just count how many Beaver triples you would need, do it for some number, and just extrapolate. Because they're all independent. If you have just a lot of machines, you can do them all in parallel, but to be fair, everything here is, I think, like single-threaded and yeah, local, not locally. These results here are all for 2 parties. 2. Yeah, because also this paper that we compared to only did 2 parties. So we have, like, in the paper, we have also some benchmark for 4 parties and 4 parties overdrive, but I don't have them in the presentation, so I don't know by heart. Yeah, and then another thing you have to do for the preprocessing is so-called sacrificing. So if you have maliciously acting parties, they might just do something else instead of multiplying with what they're supposed to do. And then your relation, like C is A times B for normal Beaver triples, just doesn't hold anymore because they did something else, they added something, they multiplied by something else. So what Speeds does is so-called sacrificing. They produce 2 triples. Then they open basically masked versions of A and B and do this check. And in the paper they argue why if you check this, that what comes out here is 0, then it's very probable that one of the triples is valid, and then you just use the first triple and throw away the second one. So basically, you just do your more or less semi-honest triple generation protocol and just twice and check with the other one and use half of them. Then later the mascot protocol, here in the second triple is partially correlated to the first one, so the second component is the same. Then you can open less, and also generating the partially correlated triple is a bit cheaper. But yeah, we have a paper where we argue if you do what you do anyway in overdrive and combine things strategically, so combine the part where you authenticate for the MAC check and where you do the multiplication for the triple, you can avoid the whole sacrificing technique. So that saves you even more. So for that, we just assume first here for presentation that we have some subprotocol where we do some kind of multiplication, where as input you have like encrypted shares of X and shares of Y, and the output is shares of X times Y. But it doesn't have to be correct, it can introduce an error. So usually that's like what we use here would be the low gear subprotocol. Then the first step is we let the parties do like a zero knowledge proof and broadcast encryptions of the shares of the MAC key. And then in a triple generation, every party locally samples their own share of A and B. They use this multiplication subprotocol to multiply the encrypted MAC key share with B to get their part for the authenticated triple. So now at this point, B should be authenticated, but a party could cheat and then you have like an additive error. Then, or just parallel with the first part, you generate the encryptions of the share of A and broadcast that so everyone has it available to do in the next step another multiplication with that, with this multiplication subprotocol. Here you use the encrypted shares of A as the encrypted part, and the share of alpha, the share of B, and the share of alpha times B as the second part. So you can just here use like an extended version of this multiplication protocol, or you just run it 3 times with these 3 things. And yeah, in a normal case, you should get like then the MAC version for alpha, your C, so A times B, and also the MAC of alpha all in one step. And now what we do instead of the sacrificing is we just generate a new value and open a linear combination of all the values. So we just take all the triples, say there's 3 values, and concatenate them to like a random linear combination, open that, and do a MAC check on this. And in the paper, we argue why now every time you would try to cheat in one of the multiplication protocols, it would also make the MAC check fail. So you don't need another check like the sacrificing, but this one MAC check at the end is enough. Yeah, the idea is basically if you would cheat if you would use like, you get a wrong triple if you have like an inconsistent B in the first and second multiplication protocol. But if you use a different B in the second multiplication protocol, also your the MAC on A times B would be wrong unless you take these consistent. And if you take them consistent, so you take the B and the alpha times B consistent, then the MAC check would not fail. But if you take them consistently, then they are multiplied by the same value, and that means you get a consistent triple. You get A times B and A times B times alpha, which means the MAC check doesn't fail. Yeah, that's the basic idea here. And also, yeah, here we see how that affects the communication cost. So the first one is the standard beaver triple. The second one is the overdrive protocol with our optimization to avoid the sacrificing. So you see that it basically saves 2 times the communication because you don't throw away half of the triples. And yeah, here we again look how you would apply this for a matrix version, because in the previous slide that was for the scalar case, but you can use the same technique for matrix multiplication or convolutions. So yeah, again, you save around 2 times by doing the technique compared to normal one, but also if you use some better packing for the matrices, you save like here factor 1.6 compared to the matrix previous state of the art. Yeah, and again, in the runtime, that's also faster. Here now we skip the line where we did the second version of the overdrive protocol because it's still much slower than doing the matrix-based version. And yeah, here also we use like a different matrix packing, so that's much faster because we only do like plain text ciphertext multiplications for this matrix multiplication, and related work as ciphertext multiplications and rotations. They're more demanding to run, so the runtime is here 4 times slower than ours. And yeah, the normal beaver triples again much slower because you have to generate much more beaver triples. And also similar results for the slower network, where the beaver triple is just getting more and more unpractical, and still we are better than the other matrix approach. So overall, if you use these specialized techniques, you have a more efficient offline phase for any type of beaver triples. One part is by avoiding the sacrificing. We also have a paper where we do that for plain text modules that is like for integers, so to the decay, not prime modules, because there it turns out it's a bit harder to do the whole technique, so you'd have to use some special tricks to get the same, but it still works. Yeah, we have new methods for how we can pack in matrix multiplications and convolutions, and yeah, one big gain in efficiency is by not doing as many heavy ciphertext operations, but keeping it to like simpler plaintext ciphertext operations. Yeah, also this is the first actively secure MPC protocol that directly does the convolutions without going through matrix multiplications. We get some gains there. And then makes overall also the same for the matrix things. It makes the offline phase faster and the online phase faster. So overall, it's a gain if you use these kind of techniques. Yeah, and also we considered some types of convolutions that others didn't consider before. Yeah, and also, like I said before, you can do pairs for matrices. That's like something, multiply a matrix by the transpose of the same matrix. You can use that in some use cases. And we have some specialized protocols here because the inputs for the multiplication for the left side and the right side are partially the same, so you can save some operations there. Yeah, that's it for my talk. You can check out the papers and ask questions. Thank you.